In the heart of Africa flows a river so powerful that every second it discharges tens of thousands of cubic meters of water into the Atlantic Ocean. Thousands of kilometers away, the Sahara is encroaching on former agricultural lands while Lake Chad struggles to survive. For decades, engineers and governments have been studying an extraordinary idea: capturing a portion of the Congo Basin's water, channeling it north, and using it to rebuild lakes, crops, and green corridors in the driest regions of the continent. The project would require canals longer than some countries, enormous dams, and agreements between numerous nations. Its scale seems like something from a future civilization. Yet, its plans began to take shape more than 40 years ago. The central question remains, can the Congo River truly bring life back to the Sahara? The Congo River traverses the African continent in a vast arc before emptying into the Atlantic Ocean. Its basin covers over 3.5 million square kilometers and extends across territories of the Democratic Republic of Congo, the Republic of Congo, Angola, Zambia, Tanzania, Cameroon, Burundi, Rwanda, and the Central African Republic. The main channel receives water from a gigantic network of tributaries. Some originate north of the equator and others south, a distribution that partially compensates for seasonal variations. When rainfall decreases in one area, other regions of the basin can continue to contribute to the flow. This characteristic makes the Congo one of the most consistent and voluminous rivers in the world. Near its mouth, the average flow rate is around 40,000 cubic meters per second, although measurements vary depending on the location, the time of year, and weather conditions. Only the Amazon River carries a greater volume. A considerable portion of this water comes from rainwater recycled by the rainforest, inland swamps, and humid air masses circulating over Central Africa. The Congo rainforest functions as a vast biological infrastructure. Trees absorb water from the soil and release it into the atmosphere through transpiration. The vapor forms clouds, fuels further rainfall, and maintains a dynamic circuit connecting vegetation, soil, rivers, and the atmosphere. Large wetlands store water during the rainy season and release it slowly, buffering flow fluctuations. Within this system lies the Cuvette Centrale, an extensive depression covered by swamp forests and peat bogs. Beneath its surface lie enormous reserves of organic carbon. The stability of this territory depends on the permanence of water and a delicate balance between flooding, vegetation, and temperature. The Congo, therefore, represents much more than a river carrying water to the sea. It is the main artery of a complex ecological system that influences the regional climate, maintains extraordinary habitats, and sustains millions of people. At first glance, its flow appears so abundant that removing even a small fraction might seem insignificant. This impression gave rise to numerous proposals for water transfer. If the river discharges tens of thousands of cubic meters per second into the Atlantic, diverting some of it to a dry region might seem like a logical way to redistribute a poorly distributed resource. However, the Transaqua project doesn't propose installing a pipeline at the river's mouth and pumping water north. That solution would require lifting the water more than 1,000 meters and transporting it over an immense distance, with virtually unmanageable energy consumption. The proposal seeks to intercept several northern tributaries of the Congo River before they reach the main channel. Rivers such as the Ubangui, the Koto, the Mbomu, the Uele, and other waterways in the northeastern region are among the alternatives being studied. Many flow relatively close to the watershed separating the Congo Basin from the Chari Basin, the main source of water for Lake Chad. The topography would allow part of the water transfer to be done by gravity, reducing the need for continuous pumping. In its most ambitious version, Transaqua envisions building dams on several tributaries, regulating their flows, and collecting some of the water in a navigable canal approximately 2,400 kilometers long. The waterway would follow contour lines until it crosses the watershed. Then, the water would flow down into the Chari River Basin and eventually reach Lake Chad. The canal would serve several simultaneous functions: as a water conduit, an inland navigation corridor, a source of hydroelectric power, and a hub for new agricultural activities. Some historical accounts envisioned parallel roads, ports, industries, and cities distributed along its route. Its aim would be to transform an isolated strip of Central Africa into a transcontinental economic corridor. Agricultural products could be transported by water, dams would generate electricity, and inland areas would gain a connection to distant markets. The transferred water would support new irrigation projects in the Central African Republic, Chad, and other Sahel territories. The proposal was developed during the 1980s by the Italian company Bonifica. Since then, it has resurfaced periodically at international conferences, government meetings, and in preliminary studies. The Lake Chad Basin Commission supported the exploration of interbasin transfers, and in 2018, agreements were signed to advance feasibility studies. Even so, construction of the massive project remains far from beginning and continues to be fraught with technical, financial, political, and environmental questions. The central mystery lies in its scale. A canal visible from space would traverse rainforests, savannas, rivers, and regions with limited infrastructure. It would have to operate for decades in territories affected by conflict, erosion, sedimentation, and extreme climate change. It would also require unusual international cooperation. The water would originate in one group of countries, flow through others, and produce benefits in different regions. Each government would have grounds to demand electricity, roads, navigation rights, financial compensation, and environmental guarantees. The Congo has enough water to inspire grand dreams, but its apparent abundance masks a complex reality. Every cubic meter serves a purpose before reaching the ocean. It maintains wetlands, transports sediment, allows fish migration, regulates the salinity of estuaries, and sustains riverside communities. The physical possibility of extracting the water is only the beginning of the problem. The primary destination of the diverted water would be Lake Chad, located in a shallow depression between Chad, Cameroon, Nigeria, and Niger. Unlike lakes surrounded by mountains, its contour can shift tens of kilometers with only slight variations in water level. A difference of just a few meters transforms open areas into swamps, islands, or plains covered with vegetation. The lake lacks a permanent outlet to the sea. Water arrives mainly through the Chari and Logone river system. It is then lost through evaporation, infiltration, and human consumption. This condition makes the lake an immense indicator of the balance between the tropical rains of the south and the aridity of the Sahara. Its history demonstrates that it was never a stable body of water. During the so-called African humid period, which began after the last ice age, monsoon rains penetrated much further north. At that time, there was Mega Chad, an inland lake that may have covered hundreds of thousands of square kilometers. Its surface area was comparable to that of some present-day seas. Evidence of that past appears in ancient sediments, raised beaches, shell deposits, and abandoned riverbeds. In areas that now receive very little rain, signs remain of rivers, wetlands, and human communities that once lived surrounded by aquatic life. The change began when variations in Earth's orbit gradually reduced the amount of solar radiation reaching the northern hemisphere during the summer. The African monsoon weakened, rainfall shifted southward, and the enormous lake fragmented. The Sahara gradually acquired its present appearance. Contemporary Lake Chad represents the last visible vestige of that wet era. Its existence depends on rainfall hundreds of kilometers to the south, especially in the highlands that feed the Chari and Logone rivers. During the 20th century, the lake underwent a rapid transformation. In the early 1960s, a relatively wet period allowed its open surface area to reach approximately 25,000 square kilometers. Droughts in subsequent decades drastically reduced water inflow. At the same time, withdrawals for irrigation, urban water supply, and agriculture increased. Satellite images showed a dramatic reduction in open water, a phenomenon often described as a loss of nearly 90%. However, this figure needs context. The lake is extremely shallow and consists of open water, marshes, channels, islands, and flooded vegetation. Measuring only the free surface area can give the impression that it has almost disappeared, although a significant part of the system continued to exist as a seasonal wetland. Recent studies show a more complex evolution than a linear disappearance. After the major droughts of the 1970s and 80s, some areas recovered water during rainy periods. The southern sector maintains a more consistent presence, while the northern sector fills only when water levels allow it to pass through a natural barrier known as the Great Barrier. The real crisis lies in the instability. Farmers, fishers, and herders must adapt to a constantly changing landscape. An arable area can flood one season and dry up the next. A fishing channel can become blocked by vegetation. An island can become connected to the mainland, altering routes, borders, and land rights. Tens of millions of people live around the basin. Agriculture, livestock farming, and fishing depend on the water cycles. The shrinking of the lake also coincides with rapid population growth, soil degradation, poverty, human displacement, and armed conflict. Competition for fertile land and water sources increases tensions between communities that use the same territory in different ways. The Lake Chad Basin Commission is currently working on projects for conservation, water management, regional stabilization, and the restoration of the system's ecological and economic functions. These initiatives demonstrate that the problem requires multiple actions, not just a future transfer from the Congo. The idea of filling the lake is compelling because it offers a visible solution. The diverted water would expand the flooded area, stabilize some canals, and potentially increase availability for irrigation. A steady inflow would also reduce dependence on erratic rainfall. However, filling Lake Chad is like pouring water onto a giant hot plate. In much of the region, potential evaporation can exceed 2,000 millimeters annually. A larger body of water would expose a greater surface area to the sun and wind, increasing atmospheric losses. For this reason, the success of Transaqua would depend on the volume transferred and how it is managed. A small contribution could disappear through evaporation or be quickly absorbed by new agricultural demands. Too large an influx would disrupt wetlands, settlements, and ecosystems adapted to the shallow lake. The goal would not be to reconstruct the prehistoric mega-Chad. To reclaim an area of hundreds of thousands of square kilometers would require flooding cities, roads, fields, and territories inhabited by millions of people. The realistic goal would be to stabilize certain areas of the lake and ensure a more predictable flow. This distinction is crucial. Restoring life to the Sahara does not mean turning every dune into a rainforest. It means restoring ecological corridors, grasslands, wetlands, and agricultural land in the transition zone between desert and tropical savannas. The transformation would begin in the Sahel, a semi-arid belt stretching from west to east across the continent. There, a few hundred millimeters of additional water can separate productive soil from degraded land. The Congo's water would have its greatest impact in this climatic frontier, where vegetation can still respond quickly. Lake Chad would act as a reservoir, regulator, and distribution center. From its shores, secondary canals, irrigation projects, and water supply systems could be developed. The wetlands would attract birds, fish, and livestock. Vegetation would reduce erosion and help stabilize the soil. Even so, water alone lacks the power to rebuild a region. Irrigation applied without drainage can accumulate salts and turn fertile land into barren surfaces. Agricultural expansion can destroy wetlands. Large reservoirs can displace populations and promote diseases transmitted by insects or aquatic snails. Lake Chad demonstrates that the boundary between recovery and degradation is extremely thin. An increase in flow could sustain millions of lives, but poor planning would create new conflicts over control of canals, land, and dams. The question then ceases to be how much the lake can grow. The real challenge is deciding who would control the water, how much each territory would receive, and which ecosystems would have to be sacrificed to keep it flowing. The idea of conveying water from the Congo Basin to Lake Chad stems from a fundamental characteristic of African geography. A watershed divide separates the streams flowing toward the Atlantic from those that end in the closed Chad Depression. In several areas, this divide crosses plateaus and savannas relatively close to the northern tributaries of the Congo River. Transaqua would take advantage of this feature through an extensive network of interconnected structures. The most well-known versions of the project propose intercepting part of the flow of several rivers, storing it in reservoirs, and conveying it through a canal approximately 2,400 kilometers long to the headwaters of the Chari River. From there, the water would follow natural channels toward Lake Chad. The proposal does not involve diverting the main flow of the Congo River. The Great River is too far away, flows through low-lying areas, and carries a volume that is impossible to economically pump to the Sahel. Water would be drawn from tributaries located at higher altitudes, especially in the northern and eastern regions of the basin. The canal should carefully follow the contours of the land. Each section would need to maintain a sufficient gradient to allow the water to move by gravity, but gentle enough to prevent destructive velocities. Excessive slope would erode the walls, carry large amounts of sediment, and damage the locks. Insufficient slope would produce stagnant water and necessitate the installation of pumping stations. The design would include regulating dams that would store part of the flow during the wet seasons. These structures would reduce seasonal variations and allow the canal to remain operational during dry periods. Some dams could also generate electricity by harnessing the elevation changes along the route. Hydropower would play a strategic role, supplying pumping systems, cities, industries, ports, and irrigation networks. In areas where large communities still lack a stable electricity supply, the construction of power plants could transform regional economies long before the water reaches Lake Chad. The canal would also be navigable. Cargo barges could transport grain, construction materials, machinery, and minerals between regions that currently rely on expensive or seasonal roads. The Central African Republic and inland areas of the Democratic Republic of Congo would gain a trade route to the north and west of the continent. This combination of water, transport, and energy explains why Transaqua is often described as a development corridor and not just a hydraulic engineering project. Its proponents argue that the canal could integrate separate markets, reduce the isolation of rural communities, and encourage the emergence of industrial centers near reservoirs. The project, however, remains in a phase of studies and debates. The scale of the works, their potential impacts, and the complex relationships between the countries involved prevent it from being treated as an immediate construction project. The 400-kilometer canal remains a proposal, although it has received political support and has been part of agreements aimed at assessing its feasibility. The first difficulty would be to know precisely how much water can be diverted without harming the donor basin. Average figures for the Congo River create a sense of abundance, but the chosen tributaries exhibit much greater variations than the main river. During a regional drought, the available volume could decrease just when the Sahel needs more water. Each dam would modify the natural dynamics of the affected river. Reservoirs would retain sediments that normally fertilize floodplains. They would also alter water temperatures, fish migration routes, and the seasonal rhythms that regulate the reproduction of numerous species. Large tropical rivers rise and fall according to rhythms that organize all life around them. Floods connect lagoons, floodplains, and secondary waterways. Fish enter areas temporarily covered by water, feed, and reproduce. When the water level recedes, they return to the main channels and sustain fisheries upon which entire communities depend. A dam that releases a uniform flow can efficiently produce electricity, but it eliminates some of that variability. The current continues to exist, though it no longer behaves like the river to which species adapted over thousands of years. Canal construction would also open a continuous strip across largely undisturbed territories. Service roads, camps, ports, and power lines would facilitate access to previously isolated forests. This new connectivity could boost legal trade, but also illegal logging, uncontrolled mining, poaching, and land grabbing. Another challenge would arise from the climate itself. Tropical rains can erode banks, fill channels with mud, and damage incomplete structures. Aquatic vegetation would grow rapidly in slow, warm waters. Floating plants could clog locks, reduce circulation, and increase water loss through evapotranspiration. Maintenance would be as important as construction. Thousands of kilometers of canal would require constant dredging, dam monitoring, gate repairs, and invasive species control. A prolonged interruption in a critical section could reduce the flow of the entire network. Security would add another layer of difficulty. Some areas traversed by the project have suffered from armed conflict, displacement, and a weak institutional presence. Protecting such extensive linear infrastructure would require stable agreements, coordinated forces, and mechanisms to prevent water control from becoming a tool of political pressure. Funding would have to be sustained for several decades. The final cost would depend on the route, the number of dams, social compensation, hydroelectric plants, and complementary infrastructure. Estimates cited for the project have reached tens of billions of dollars, but a definitive assessment would require much more detailed topographic, hydrological, geological, and environmental studies. A project of this scale also could not depend on a single country. Water would be drawn from territories belonging to certain nations, flow through others, and directly benefit communities much farther north. Donor basin states might consider it unfair to bear the impacts while others reap the main benefits. The distribution of electricity, navigation revenues, and agricultural land would have to be negotiated before construction began. It would also be necessary to establish rules for droughts. During periods of reduced water flow, each country would try to protect its own cities, crops, and power plants. Transaqua would transform water into a central element of African politics. Its operation would depend on treaties that could survive changes in government, economic crises, and regional conflicts. Cement might last for a century, while human agreements would need to be continually renewed. Even overcoming these difficulties, the arrival of water to Lake Chad would represent only one stage. To produce a lasting recovery, the flow would have to be distributed through efficient irrigation systems, drainage networks, ecological reserves, and regulations limiting withdrawals. Without these measures, the increased supply would generate an immediate expansion of demand. New fields, cities, and livestock farms would consume the additional water. The lake could receive a large influx and continue to be subjected to increasing pressure. This phenomenon occurs in many arid regions. When a water source is expanded, so does the economic activity that depends on it. After a few years, consumption again reaches the available limit. The initial solution creates a new scarcity on a larger scale. The true design of Transaqua would have to extend far beyond the canal. It would include institutions capable of measuring every extraction, protecting environmental flows, resolving disputes, and adjusting deliveries to weather conditions. The visible structure would be a waterline crossing Africa. The crucial structure would lie in the agreements, sensors, regulations, and agencies responsible for managing it. The Congo's water would have its greatest transformative potential in the Sahel, the strip bordering the southern edge of the desert that still receives seasonal rainfall. The Sahel is a transition zone. To the north, desert landscapes dominate, with scarce and irregular rainfall. To the south, savannas appear where the wet season allows for the growth of grasses, shrubs, and scattered trees. Between these two landscapes, small differences in rainfall and soil conservation produce enormous changes. A territory that receives 200 millimeters of rain per year behaves very differently from one that receives 400. This difference can determine the presence of permanent pastures, dryland crops, or bare surfaces exposed to the wind. The transferred water could reinforce this strip through canals, reservoirs, and irrigated areas. Instead of creating a single inland ocean, it would be more efficient to distribute the resource in productive corridors near settlements. Irrigated areas would allow for the cultivation of cereals, legumes, fruits, and vegetables for longer periods. Production would no longer depend entirely on an increasingly variable rainy season. Greater food security would reduce the need to sell livestock or abandon communities after a drought. Reservoirs and canals could also support forest belts. Trees adapted to dry environments would stabilize the soil, reduce wind speed, and provide shade, fruit, timber, and fodder. Their roots would improve infiltration and help conserve moisture around crops. However, planting trees in the Sahel requires much more than water. Each species needs temperatures, soils, and groundwater depths compatible with its physiology. Uniform plantations often suffer from pests, fires, and high mortality. Mixed systems, composed of crops, shrubs, and native trees, offer greater resilience. Land reclamation also depends on soil condition. In many degraded regions, rain falls on a hardened surface and runs off before infiltrating. Harvesting techniques, such as small ditches, earthen crescents, terracing, and planting pits, slow water runoff and concentrate nutrients. These interventions may seem modest compared to a continental canal, but they determine the amount of vegetation that each cubic meter can support. A massive project distributing water through open flooding would lose a considerable amount to evaporation. A drip irrigation network, covered reservoirs, and adapted crops would produce more food with a smaller volume. The World Bank and regional organizations have promoted an irrigation strategy for the Sahel that combines public investment, farmer-managed systems, and models adapted to each landscape. This approach reflects a crucial reality. Expanding irrigation requires institutions, maintenance, access to energy, rural financing, and markets capable of absorbing the production. The arrival of water could create a virtuous cycle. Crops would cover the soil, reducing erosion and adding organic matter. Vegetation would increase surface roughness and mitigate dust storms. Trees would release moisture into the atmosphere and create cooler local environments. On a small scale, these effects can modify the microclimate. A vegetated surface absorbs and distributes solar energy differently than bare ground. Some of the heat is used to evaporate water, reducing the temperature near the ground. Shade protects moisture and allows for the activity of microorganisms. On a regional scale, the relationship becomes more complex. Vegetation can promote moisture recycling, but it needs to receive water first. The atmospheric circulation of the Sahara is dominated by much larger systems, including the West African monsoon, subtropical anticyclones, and Atlantic temperatures. An irrigated corridor could increase local humidity without profoundly altering the climate of the entire desert. Transforming the Sahara would require altering atmospheric processes that operate across millions of square kilometers. Africa's own past demonstrates that a green Sahara requires favorable planetary conditions. During the African humid period, changes in Earth's orbit intensified monsoon rains. Vegetation expanded because it received precipitation over a vast area. A modern canal lacks the volume necessary to replicate that mechanism. The difference can be measured by the water balance. A single millimeter of rain over 1 square kilometer is equivalent to 1 million liters. If one were to try to add just 100 millimeters annually over 1 million square kilometers, 100 billion cubic meters of water would be needed. The Sahara covers an area of nearly 9 million square kilometers. Artificially maintaining a moderate amount of vegetation across a significant portion of the desert would consume volumes comparable to those of some of the largest rivers on the planet. Furthermore, much of the water would evaporate before it could produce biomass. High temperatures, dry air, and strong winds draw moisture from soils, plants, and reservoirs. Each hectare of cultivated land would require repeated applications. For this reason, the project would have to concentrate on selected areas. Valleys, depressions, abandoned riverbeds, and more fertile soils would offer better results than large dune fields. Shifting dunes have few nutrients and a low water retention capacity. Intensive irrigation would allow for the temporary growth of some plants, but maintaining them would require a constant supply. When irrigation ceased, vegetation would regress. The ancient floodplains of the Sahel offer more favorable conditions. Many contain fine sediments, shallow aquifers, and communities accustomed to combining agriculture, fishing, and grazing. There, an additional flow could multiply productivity without constructing a completely artificial system. The water could also recharge aquifers. Unlined canals would lose some of their contents through seepage, a phenomenon considered inefficient from a transport standpoint but potentially useful for raising groundwater reserves. Nearby wells would retain water for longer periods, reducing reliance on open reservoirs. Recharge would need to be carefully monitored. An excessively high water table can bring mineral salts closer to the surface. When the water evaporates, the salts become concentrated in the soil and gradually reduce its fertility. Salinization represents one of the greatest dangers to agriculture in arid climates. Irrigation water always contains dissolved minerals. In humid regions, rain washes these minerals into deeper layers. In the Sahel, evaporation removes the water and leaves the salts accumulated around the roots. Irrigated land needs drainage. A network of secondary canals must remove excess water and maintain the water table at a safe depth. The drained water contains salts and requires controlled disposal because returning it directly to lakes or rivers can degrade other ecosystems. Intensive agricultural production would add fertilizers, pesticides, and organic waste. If these substances were to reach Lake Chad, they would stimulate excessive growth of algae and aquatic plants. Decomposition would consume oxygen and harm fish and other species. The recovery of the Sahel would therefore depend on agriculture designed for dry regions. Resistant crops, crop rotation, localized irrigation, agroforestry, and soil conservation would be more valuable than simply expanding large monocultures. It would also be necessary to protect the mobility of pastoralists. For centuries, numerous communities have moved their flocks following the rains and the seasonal availability of pasture. New fields and canals could block traditional routes and concentrate animals in smaller areas. A poorly planned green corridor would create fences, disputes, and loss of access to water. An integrated system would reserve livestock crossings, watering points, and connected grazing areas. Life returned to the Sahara would not belong exclusively to agriculture either. Seasonal wetlands would support fish, migratory birds, reptiles, and insects. Some canals could become new ecosystems, while others would facilitate the spread of invasive species and diseases. Permanent water favors mosquito breeding. Reservoirs and slow-moving canals can also expand the habitat of snails that transmit parasites. Agricultural benefits would have to be accompanied by health monitoring, sanitation, and biological control. The most realistic outcome would be a mosaic. There would be supplied cities, areas of intensive cultivation, agricultural forests, restored pastures, and protected wetlands. Dry expanses, dunes, and desert landscapes would continue to exist between them. This mosaic could sustain millions of people without erasing the Sahara's natural identity. The great transformation would occur at its edges, where the desert advances or retreats depending on the balance between water, vegetation, and human activity. Transaqua could fuel this process, but it would never act in isolation. The canal would carry water. Its recovery would depend on how every drop was used after crossing the continental divide. The Congo River has an extraordinary flow, and its relative proximity to the headwaters that feed Lake Chad makes water transfer a technically conceivable possibility. Projects like Transaqua demonstrate that the idea transcends the realm of fantasy. There are studied routes, proposals for dams, navigable canals, hydroelectric plants, and connections to the Chari River. However, the capacity to construct such a project does not guarantee its success. The water would have to travel thousands of kilometers, cross several countries, and remain within a system subject to sedimentation, evaporation, political instability, and high maintenance costs. Each dam would alter the dynamics of the Congo's tributaries, while each new irrigated area would increase future demand. The main limitation lies in scale. The Sahara covers millions of square kilometers and loses enormous volumes of water through evaporation. No canal could transform the entire desert into a green expanse without extracting quantities capable of severely damaging the donor basin. The image of a Sahara once again covered by forests, lakes, and savannas belongs to a climate transformation far larger than any engineering project. The most realistic impact would be concentrated in the Sahel and the Lake Chad Basin. There, additional water flow could stabilize wetlands, restore pastures, expand agricultural areas, and reduce the vulnerability of communities subjected to recurring droughts. The water would also allow for electricity generation, improved inland navigation, and the connection of currently isolated regions. These benefits would depend on rigorous management. Irrigation would require drainage to prevent salinization. New fields would have to respect livestock routes and natural ecosystems. Reservoirs would require health monitoring, while the countries involved would have to agree on how to distribute the water, electricity, and revenue generated. Protecting the Congo Basin would also be essential. Its rivers support floodplain forests, fisheries, peatlands, and communities that depend on seasonal floods. Extraction calculated solely based on average flow would ignore essential ecological functions. Before building the canal, it would be necessary to determine how much water can be withdrawn during each season without compromising the stability of the system. The final answer contains two realities. The Congo River could help revitalize degraded regions of the Sahel, replenish Lake Chad, and create productive corridors on the edge of the Sahara. However, it lacks the volume necessary to permanently reforest the entire desert. The region's future will likely depend on a broader combination of factors. Water transfer could work in conjunction with soil restoration, agroforestry, rainwater harvesting, efficient irrigation, solar energy, and sustainable aquifer management. No single measure will solve a challenge comprised of climate, poverty, population growth, and environmental degradation. Transaqua represents one of the most profound decisions Africa could make about its own geography. Its construction would link two of the continent's largest river basins and alter territories for generations. Implemented with scientific knowledge, international cooperation, and strict environmental constraints, the project could transform a part of the Sahel. Implemented as a simple water extraction project, it would merely shift the crisis from one region to another. The Congo retains the capacity to fuel a limited and strategic recovery. The real question is no longer whether water can reach the Sahara, but whether the societies responsible for channeling it can use it without destroying the system that produces it.